let's go to the second one. If you plug in the r equal -1 to the equation, it's more interesting. Put the -1, 1 minus -1 is 2, 2, 2. You got a 2, 2, 2 on the major diagonal here. And then that's what we have, 2, 2, 2 here. Well, in this system, you really only get one equation. Why? If you look at the second one, it's -1 of the first one. The third one is exactly the first one. Now, if we let the first row add to the second row, you get a 0, 0, 0 here. And the third row minus the first row, you get a 0, 0, 0 here. So the last two is useless. What is the rank we talked before? The rank is going to be 1. You only got a 1 non-zero. And then what is the freedom? How many freedoms? The freedoms is 2. You have 2 free choices. So let me write the first equation. That's the only thing matter. Okay, that's positive. And take 1 away, u1 equals u2 minus u3. You got 2 freedom. I can let the u2 equal t, u3 equal s, then u1 equals t minus s. Yes. And then your solution will be v equals t minus s, t and s. Let me rewrite it. Rewrite it t, t0 plus -s, 0s. Take the t out. And the 1, 1, 0. And take the s out. And the -1, 0, 1. Well, I don't need this t and s. To make it easier, I have 2 eigenvectors. Let the t equal 1, s equal 0. I get the first one, this. And now let the t equal 0, s equal 1. I get the second vector equals -0, 1. From the previous lesson, we understand this is a 2D plane. A 2D plane, you can select infinite many different vectors to make it a plane. I only need to select 2. The bottom line is the 2 cannot be parallel. If they're not parallel, we call it linearly independent. They're going to combine with the t and s to make the whole plane. So this time, we got 2 linear independent eigenvectors, v1 and v2, to associate the same eigenvalue r equal -1. So how many we have total together? 3. Because the n equals 3, I need 3 of them. This is one, this is another one, and the third one is here. We have 3 of them. That's very good. For a lot of computation, if you have 3 eigenvectors for the 3 by 3 matrix, the job will be really easy. We're going to see next hour. So let's look at another concept. If you look at this plane, add the 0 eigenvector, 0 is another eigenvector, it's always satisfy the equation. You get the complete plane. You know, you let t equal 0, s equal 0, you can get 0, 0, 0. Anyway. So this plane is made by the 2 vectors, 1, 1, 0, 1, 1, 0, this vector. Let me put another color. And another vector, 1, 0, and -1, -1 here, and 0 in y, and the 1 in here, z, that's another vector. So these two vectors make a whole plane. This plane we have a name because made by the two eigenvector, we call it eigenspace. Eigenspace is a 2D space. So it's just a name to tell you, and these eigenvectors make their own space. So what we hope is when you have n equals 3, you have n eigenvectors independent. If n equals 2, you get 2 independent eigenvectors. N equals 4, you get 4 independent vectors. Then the space is like completely equal the dimension you have to start with. Unfortunately, this is not always true. And for those who cannot find enough eigenvectors, we call it defective. Now we are going to define the name called defective matrix. But we can guarantee it be true when the matrix is symmetric. We have another example. I'm going to run quickly. Again, is a symmetric matrix. I found the two eigenvectors only, and this number that equal 1 is again a repeating eigenvector, and the number that equal 10 is a single eigenvector. And then you put the number that equal 10, you solve this one, and what we found is this solution. The difference from the previous example is this time I used the Gauss-Jordan algorithm to solve it. I used the Gauss-Jordan algorithm. The advantage is I can clearly demonstrate this is a singular matrix and the rank equal 2. Then I have one freedom just to repeat what we did before. So what I did is first divide by 2 to make this 1, and then put this in the first row and swap the first row to the third row. And this element, we call it the pivotal element. And use the pivot element, I add the negative 4 times of the first row to the second row to make the nice 0 here. Add the 5 times of the first row to the third row, I add the 0 here. When I finish this job, I observe that the second and the third is really the same equation, different by a negative 1. If I add the second to the third, I get all 3 zeros. So now you understand the rank of the matrix is equal to, and I have 2 independent equations. The second one is negative 9 B2 equals 18 C2, and then B2 equals negative 2 C2. I will let the C2, positive. C2 equal 1, then B2 equal 2. Now go back to the first equation. We got this one, A2 plus B2 minus 4C2 equals 0. Then the A2 equals 4C2 minus B2 equals 4 minus 4C2. 4 minus, wait a moment, which one I got? B2, C2, I need A2. A2 plus, it's a 4C2 minus B2. It's a 4 minus 2 is 2. Not a negative 2. Did I make a mistake? 1, 2, 3. C2 equal 1, B2 equal negative 2. I think this is 2 then. So your eigenvector is 2, 2, 1. Well, in the old time, I usually choose this C2 equal T, then your B2 equal 2T, and then your A2 equal 4T minus 2T is 2T. Same thing, just factor out the T. Again, I said I don't concern the lengths. All I need is the direction 2, 2, and 1. That's one of our linear eigenspace. The second one is more interesting. When the lambda equal 1, put back into here the 1. See, 5 minus 1 is 4, 4, 4 on the major diagonal. And what we get is 4, 4, 2, 4, 4, 2, 2, 2, 1. What does that mean? That means you only got one equation. Because you see, the first one is the double of the third one, second one is double of the third one. In all this case, I only need one equation. You can select either one, the first or the second, and we follow the same procedure. The rank equal what? 1. Oh, by the way, if you use MATLAB, just call the command rank. You can find the rank of A. This is a command. We'll find the rank. The rank means how many independent equations you really have. Just one in this case. If rank equal 1, the freedoms equal what? Number of variables minus the rank is 2. You have 2 freedoms. Then you can let the second variable equal t, third variable equal s. Oh no, the first equal t, second equal s, then the third equal negative t minus 2s. Now ts negative 2t minus 2s, I can rewrite it as this vector. Again, you have 2 independent vector. This is a plane in 2D. It's a span, we call it a span, made by the 2 vectors. Now, demonstrate one more time. If you get any plane, you can select any 2 not parallel vectors to make it a plane. Then the rest of them, just select the s and the t, you can fill the whole plane, the plane. So that's the eigenspace. It's 2D. The last example I want to show you is a defect matrix. What's one of that defect? Well, when we look at the eigenvalues, start from the characteristic equation, a little calculation, we find this interesting. We got the triple root. This triple root means you only got one eigenvalue. All numbers equal 1, equal 1, equal 1, equal 1. So it's impossible for anybody from the equation to find a 3-dimensional eigenspace. How much you can have? Let's just try to find the eigenvector. Replace this by negative 1, negative 1. The number equal 1 because it's 0 minus lambda. That's 3 negative 1. And assume the eigenvector is A, B, C. The rank of the matrix is 2. You clearly see the first and the third are 2 different equations. You got the negative A plus B equals 0, and the negative B plus C equals 0. Well, I can see the B equals A, and the B also equals C. And if you let the B equal 1, you only got the A and the C also equal 1. So that's the only eigenvector you have. Or you make it a little longer, it's still what we call a linear eigenspace. Means the spaces all stayed in the same straight line. Even you got infinite many, but in the same straight line, you still only get 1. So why is it defective? Because I'm looking for 3, I can only get 1. That's why it's defective. For those kind of matrix, if you want to try to reduce calculation in the future, it's going to be difficult.